Good afternoon. First of all, microphone, okay. Yeah, okay. First of all, I would like to thank Professor Kim and Professor OK to invite me. I really enjoyed the visit to Korea every time, and certainly more of the friendship we have over the years developed, and the friendship actually helps the science collaboration. Today I'm going to talk about a little bit focus on the cities, urbanization. Professor Wang already touched upon this topic as we are becoming more urbanized. And my background is biogeochemistry, so I try to apply what we are doing to develop sustainable cities. Just a quick overview. Probably you are all very aware of, by the end of the year 2007, globally, we are becoming urbanized. So over 50 of the world population live in the cities by that time. And also in China, traditionally as a largest agricultural society, by the end of year 2011, we also have over 50% of the population now live in the city. So that is really a dramatic demographical change, but more importantly is a societal, economic, and environmental change in the history. The urban ecosystem is so different from the natural ecosystem and the agricultural ecosystem. In the urban ecosystem, we are the dominant species. We, as us here, is a dominant species. So the ecosystem is also highly engineered. We have wastewater treatment plant. We have drainage system. They are equivalent to when the earthworm move around in the soil, like we are moving around in the urban ecosystem. So we are equal, or not equal, but we are equivalent to species like earthworm, changing the ecosystem, perturb the ecosystem. So that's why resilience, the term resilience comes in. When we perturb the ecosystem, how the ecosystem respond, how the ecosystem can recover to the initial state. So this I borrowed a slide from Resilient Cities. This is an organization, international organization about resilient cities. So when we talk about resilient cities, it's transferring some of the theoretical framework of resilient science to practice the sustainability of urban system. And this urban system is dominated by humans. And we are facing environmental, social, and economic challenges. So I think one of the characteristics of urban ecosystem or urban resilience is actually the coupling of environmental, social, and economic systems. So I think probably you are all aware of this resilience framework. I'm not going to go details, just to show you that how a system can respond to perturbance from external forces. Just to illustrate this issue a bit more, here I want to show you that the general impacts of urbanization. So we see lots of benefits of being urbanized or being in the cities. We enjoy centralized facilities, health care, sanitation. These are all positive. However, in the same time, we have some disadvantages because within the urban system, the energy and material consumption per unit land increases dramatically. So that also comes with the biogeochemical processes. So in a resilient ecosystem, the material cycling is more or less balanced. Let's say in the natural environment, the earthworms are working for us, the microbes are working for us. So it's balanced. But in the urban ecosystem, we are accumulating food and the people. And in the end, the nutrients are also being urbanized. We have accumulation of phosphorus and nitrogen in the urban environment and in the peri-urban environment. They are causing problems like the deterioration of some of the ecosystem functions. So here I also mentioned that the impervious surface, we have pavement, so the natural soil actually can filter the water. They can attenuate the contaminants, the nutrients. However, when we urbanize, there's a lot of impervious surface, and they create the problem of the hydrological cycling, flooding, and the contamination, of course. So this also impacted the aquatic environment, and also like urban transport and the fossil fuel burning, they can all release contaminants. In addition to this carbon dioxide as a global warming driving force, there are many other contaminants, and many of them are micro pollutants that Professor Wang has already talked about. I want to illustrate the issue a bit further using phosphorus, because phosphorus is critical. In my opinion, phosphorus is even more important than energy. We have the sun. We can always get energy from the sun. And we can always get some nuclides that we can produce energy from nuclear reactions. But the phosphorus is really non-renewable resources. When we explore the phosphorus deposit, we make fertilizers, we consume the food, we treat the wastewater, and the phosphorus is eventually discharged into the river, into the soil, into the ocean, or ended up in the landfill. So they are not being brought back into the food production system. So that caused the problem of non-resilient biogeochemical cycling. So this is an article in Nature a few years ago. So it's the disappearing nutrient. So, and I, with my colleague, we did some analysis. So this diagram actually visualized the problem. So our 50% population live in less than 1% of the land surface. So occupy a small area, the cities, small area. But we consume over 60% of the food, the national food. The food is there from the countryside, from far away. But we are concentrating this in this narrow, tiny place. So you can see how we are accumulating the nutrients in the urban environment. And that causes some of the problems, the non-resilient problems. Here just some pictures. If you travel in China, you often see many lakes are being eutrophicated. So alga blooming, toxic alga blooming causing the death of fish, the invasive species, aquatic plants. So this is really, I consider it as a vicious cycle of this broken, due to the broken biogeochemical cycling. So in the old traditional agriculture society, we recycle pretty much everything back to the agriculture field. However, with this modernization, urbanization, we are breaking this cycling and end up with the accumulation of nutrients in the urban and the peri-urban environment. So this is again another picture. Two pictures show you the landscape after big rain. You can see here is the flooding and this discharge of contaminants and water, wastewater from the urban environment during these events. So in China now we are promoting the idea of a spongy city. So how can we develop a city more resilient to the environmental condition? If the city can absorb the rainwater and discharge them in a more natural way, we can mitigate the environmental problems. So this is so-called the green infrastructure or nature-based infrastructure for these environmental problems. So I just want to summarize what I have just mentioned. How can we manage this biogeochemical cycling for resilient cities? First of all, we should try to understand the stock and the flows of these materials in urban and peri-urban environment, so that we can reveal the source and the fate of the contaminants and nutrients. Where are they from? Where are they going? So we have to know that. And we also have to understand the processes of the material flows, the processes, and the fluxes indeed. So this is the core issue of urban biogeochemistry. And we should also look at the landscape and ecosystem services. For example, the water quality, carbon stocks. Professor Boland will talk about the carbon sequestration in the ecosystem. And I think in this urban, peri-urban environment, those issues are also embedded in this resilience science. And of course, for urban ecosystem, food security is among the top. And here, I mean food security in terms of both quantity and quality. So food security also included issues that Professor Wang has already illustrated about the contaminants, mercury, arsenic, or other PTS in the food. And many other issues. Probably some other speakers will touch upon that, but for the sake of time, I just illustrate these issues for consideration. And how can we increase the resilience of the urban ecosystem? We know the urban ecosystem is highly perturbated and is highly engineered. How can we make it more resilient? So we proposed the idea together with Dr. Brian Reed from UEA, England. We proposed the idea of this peri-urban ecosystem. We call it pure, because essentially it can purify many of these contaminants in the peri-urban ecosystem. So this is just a diagram to show you this structure of the ecosystem, from the atmosphere to the vegetation, soil, groundwater, bedrock, and also to the surface water, surface runoff, etc. So we have roughly we have three different ecosystems. This is urban ecosystem, this is a rural-urban transition zone. So that is the one we are talking about, the pure peri-urban ecosystem. They sit at the interface between the rural natural ecosystem and the urban ecosystem. So this pure is very important because they can act as a filter. So you can see that the urban ecosystem, we are talking about the eco-infrastructure, the nature-based solution, and the cultural health, biodiversity, and these are we all probably aware. In the urban environment, we need a parkland. We need beautiful lakes because they provided amenity and provided a place that we can relax. This is becoming the ecosystem services of all these will be beneficial to urban health and well-being. However, in the pure, this peri-urban ecosystem, there can be a place for waste assimilation. I will provide some examples. Food production, water supply, and of course culture, biodiversity. You know, in the peri-urban environment, often you can set up leisure, ecological parks. People can go there, pick up fruits, make picnic. You know, this all will benefit our health and well-being. This is the rural ecosystem. It's mainly for food production, water supply, biodiversity, and also natural reserves. So this is the concept of pure. And to summarize the ecosystem services provided the pure, I can summarize here. So first of all, as I said, it can be the repository of contaminants and also nutrients for cities, probably mainly from water, air, and also waste discharge. And they are the major food source for urban populations. So, you know, if we want to have an efficient food system, you don't want your food to be transported from New Zealand or from United States. We hope we should try to produce the food locally, so the carbon footprint of the food is minimal, or it is minimized. And I think it is also the best showcase to balance different ecosystem services. We know that the ecosystem has multifunctionalities, and sometimes the multifunctionalities, they are not always in harmony. Sometimes they are in conflict, and we have to balance that. So this is called a trade-off of ecosystem services. And this peri-urban environment or ecosystem is really a place that we have to balance this, whether it is for food, whether it is for water quality, or it is for culture, leisure, health, you know. So we need to balance these ecosystem services. And in the past, I would like to say this peri-urban ecosystem is largely overlooked. And in China, it's particularly important. We are currently, the current government is very keen on this people-oriented urbanization. Because in the past, we perceive city as a place for business, for making money, for generating GDP. But in fact, we are going to the cities for better life. Better cities for better life. So urban health and well-being is a holistic view of urbanization. It's not just about money, it's about overall health and well-being. So I think this is something I want to just quickly summarize. One area is related to this resilient city is the waste reutilization and disposal and safe use. So it's a valorization of urban waste, which I think is a key to sustainable and resilient cities. However, we have lots of micropollutants in the waste stream because we are using shampoo, we are using soap every day, and we sometimes taking drugs. And these drugs and these components, these chemicals, they are discharging with the waste stream into the water, into the soil. So this has to be considered. So one of the example we have been doing in China is looking at the microbes. So you talk about other pollutants, chemical pollutants, but the microbes, they are unique. If they are acting as a pollutants, they can be amplified because they are lives. When they arrive in a new destination, they can proliferate. They just as a pollutant, as a pathogen, or as a virus, you know, they can be. So here I want to use the use of sewage sludge and the discharge of antibiotic resistance or antimicrobial resistance. We are all very aware this antimicrobial resistance is a global public health threat because we are using antibiotics too much on humans and on animals, and they are exerting as a selection pressure for the microbe. So the microbes develop resistance, and if the pathogens acquire this resistance determinants, they become superbugs. That means if there are superbugs, there's maybe little hope for treating patients. So we use this long-term experimental site to look at the accumulation of resistant genes. So these genes are actually pollutants. You can see the concentrations. With the application of sewage sludge, there is increase of these pollutants. Clearly you can see that. However, we can also turn sewage sludge into biochar. Into biochar, we can kill the microbes, and we can destroy these antibiotic compounds. So we think that turning sewage sludge into biochar is a very good way of assimilating urban waste in peri-urban ecosystem for food production. So here, this is an article we published a few years ago. You can see that this sewage sludge derived biochar can be used and to promote the growth of rice, the yield, and we still get the reasonably safe food because the biochar can sequestrate the metals and reduce the destroy the organic compound. And in this, we are collaborating with Professor Oak in this Korean biochar center. And this waste management, and I think it can be integrated into green infrastructure because this biochar you can use to improve the soil conditions. You mix the biochar with the soil, you increase the filtration. So the water can move quickly into the soil without causing flooding. And the biochar itself can retain the microbes and the nutrients. So it can act as a buffer zone for protecting the aquatic ecosystem. So this is just an example we have done in China, in Wuhan, central China. This is a city with more than 1,000 lakes. So this aquatic ecosystem is very important. So we developed some demonstration areas, improve the soil quality by improving the infiltration and the vegetation. You increase the resilience of the city. So I think there are many benefits of, or cool benefits of waste-derived biochar. Nutrient recovery, I talked about phosphorus as a crisis, but with biochar we can recover phosphorus. And also other micronutrients, silicon also. Silicon is important for rice growth. And improve soil structure, I already used some examples, eco-infrastructure, and a buffer zone contaminant attenuation. And they can also be used as novel materials, other novel materials I think we can derive. And to eliminate pathogens, antibiotic resistant genes in organic waste. So these are the benefits or co-benefits of valorization of urban waste. And also, probably you see my paper a couple of months ago, I published in Science. I talked about the microbia mass movement. So when we talk about ecosystem resilience, we often see what we can, we often talk about the system we can see with our naked eyes. However, behind this, what we see, there is a microbial world. It's invisible, but they are changing all the time, and the microbes, they travel with no boundary. So for example, when we are arriving in Seoul, we go through the custom. But the microbes, there's no custom for the microbe. They can be traveling freely around the globe. Come with the food, with the water, with our human body. We carry more cells than ourselves. When we arrive in Seoul airport, we carry more cells, more bacterial cells than our mammalian cells in our body. So the microbial world is certainly an area for investigation. So I just want to quickly go through this, just the example of the genes we are talking about. This is a gene cassette that recruit new genes and the horizontal gene transfer. And I don't want to go into details, but I welcome questions or even collaborations in the future. And how can we improve the urban ecosystem resilience? We propose that this critical zone science can actually improve the urban resilience. Because this critical zone science, we consider the coupling and the relevant and the comprehensive understanding of the whole ecosystem. So we try to put the bits of the system together, use a holistic approach. When we talk about the soil, we also should talk about the groundwater, also talk about the food. When we talk about the air pollution, also soil and water. So as a system, so systems approach is important for urban resilience. And I think critical zone science can offer some benefits or advantages. So some challenges we are facing. So how can we characterize the urbanizing critical zone? So critical zone, taking this vegetation, soil, groundwater as a system, as a together. So this is essentially the life supporting system of our planet. We talked about the planetary boundary, and this is the important boundary of the Earth system, the critical zone. And the impact of, for example, organic amendments, this carbon quality, quantity from cities and soil functions, and urban pollutants or ecosystem, human health, integrating with urban green infrastructure, and also mitigating. We should develop mitigation approaches and also modeling to predict the future changes of the ecosystem, urban ecosystem. So with that, I would like to conclude my talk. I hope that the concept of resilient city, I have emphasized that the integration and the interactions within the Earth's surface system is important as a whole rather than in pieces. At the urban-rural interface, that is a pure, biogeochemistry is critical in maximize urban ecosystem services for resilient cities. And the resource, of course, it's carried by material, recycling and recovery. It's not only an engineering challenge, but also a challenge for environmental sustainability. And I think that antimicrobial resistance can be used as an example to test our hypothesis and to also develop novel solutions. If we can solve the problem of this invisible world, probably it's easier to solve some of the problems we can see by naked eyes. And with that, I also want to thank the Natural Science Foundation of China, Chinese Academy of Sciences, and also UK, the Newton Fund, NERC, for continuous support towards my research, and also my students and colleagues in many places, international collaborators for this area of research over the years. And this is my institute, Institute of Urban Environment, and I welcome you all to my institute, and we develop joint projects. And I also want to thank you for your attention.